the Euclidean or Greek method, and I would like to say why. The problem in the Euclidean method is to make something about the axioms a little bit more interesting or important. But the question that we have is, in the case of gravitation, is it more important, is it more basic, is it more fundamental, is it a better axiom to say that the force is directed toward the sun, or to say that equal areas are swept in equal time? Well, from one point of view, the forces is better, because if I state what the forces are, I can deal with a system with many particles in which the orbits are no longer ellipses because of the pull of one on the other, and the theorem about equal areas fails. Therefore, I think that the force law ought to be an axiom instead of the other. On the other hand, the principle that equal times are swept out in equal areas are swept out in equal times can be generalized when there's a system of a large number of particles to another theorem, which I had prepared to explain, but I see I'm running out of time. But there's another statement which is a little more general than equal areas in equal time. Well, I have to state what it is. It's rather complicated to say, and it's not quite as pretty as this one, but it's obviously the son of this one. I mean, it's the offspring. If you look at all these particles, Jupiter, Saturn, the sun, and all these things going around, lots of stars or whatever they are, all interacting with each other, and look at it from far away and project it on a plane, like this picture, then everything is moving this way, and moving that way, and so on. Then take any point at all, say this point, and then calculate how much each one is changing its area, how much area is being swept out by the radius to every particle, and add them all together. But wait, those masses which are heavier count more strongly. If this is twice as heavy as this one, then this area, it counts twice as much. So you count each of the areas that are being swept out in proportion to the mass that's doing the sweeping, and the total of all of that is not changing in time. That's a generalization, obviously, of the other one. Incidentally, the total of that is called the angular momentum, and this is called the law of conservation of angular momentum. Conservation just means that it doesn't change. Now, one of the consequences of this is, just to show what it's good for, imagine a lot of stars falling together to form a nebula, or a galaxy. As they come closer in, if they were very far out and moving slowly, so there was a little bit of area being generated, but on very long arms, distances from the center, then if the thing falls in, the distances to the center are shorter now. If all the stars are now close in, then these radii are smaller, and in order to sweep out the same area, they have to go a lot faster. So as the things come in, they swirl around, and thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with the leg out, moving slowly, and as you pull the leg in, it spins faster, because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster. But I didn't prove it for the skater. The skater uses muscle force. Gravity is a different force, yet it's true for the skater. Now we have a problem. We can deduce often from one part of physics, like the law of gravitation, a principle which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be. In other words, if we were to say that the postulates of physics were this law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general conservation law of angular momentum, but Newtonian laws were wrong. There's no forces, it's all a lot of baloney, the particles don't have orbits, and so on. Yet, the analog, the exact transformation of this principle about the areas, the conservation of angular momentum, is true for the atomic motions in quantum mechanics, and is still, as far as we can tell today, exact. So we have these wide principles which sweep across all the different laws, and if one takes too seriously his derivations and feels that this is only valid because this is valid, you cannot understand the interconnections of the different branches of physics. Someday, when physics is complete, Then maybe with this kind of argument, we know all the laws, then we could start with some axioms, and no doubt somebody will figure out a particular way of doing it. And then all the deduction will be made. But while we don't know all the laws, we can use some to make guesses at theorems which extend beyond the proof. So in order to understand the physics, one must always have a neat balance and contain in his head all of the various propositions and their interrelationships, because the laws often extend beyond the range of their deductions. This will only have no importance when all the laws are known. Another thing that's interesting in the relation of mathematics to physics is this, a very strange thing, that by mathematical arguments you can show that you can start from very many different apparent starting points and come to the same thing. That's pretty clear if you have axioms, or you can use some of the theorems, but actually in the physical laws are so delicately constructed that the statements of them have such qualitatively different character that is very interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out, but they sound completely different. 1, there's the forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion, rather, at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call a non-local quality. The force on this depends on where that one is over there. Now you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing, that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical. There's a number at every point in space. Here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. That's one statement. That's not enough yet, because I have to tell you now how to determine how the potential varies. I could say the potential varies as 1 over the distance from each object, but that's back to the action at a distance idea. However, the force is at a distance, but you can state the law in another way, and it says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus this constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one, because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy in